Okay, this video now is a discussion of situations where we may have equilibrium which will involve friction. Whenever a surface is rough, we need to consider friction. Friction is a passive force. It opposes the motion of sliding but does not cause any motion. So if something is stationary on a surface, friction is unable to move that object. However, if you start to push that object across the surface, friction will act in response to your pushing. It's intuitive to us that if two surfaces are smooth or slippy even, then there is less friction between those two surfaces. It's also intuitive that the heavier an object is, the harder it is to push across a surface. We can therefore conclude from those last 2 points that friction is related to the mass of an object and the nature of the two contact surfaces, the surface of the object and the surface over which that object is sliding across. If we apply a horizontal force to an object, then we wish to push it across the horizontal surface and it does not move, it's because friction is cancelling out the push force. If we increase that push force and the object still does not move, it means friction must have increased and is still cancelling out that increased push force. However, at some point it must be possible to apply a big enough push force to get the object moving, and when an object is moving or on the point of moving, friction has reached its maximum value, and that maximum value we denote by mu r. So that is the Greek letter mu times r. R is the normal reaction and mu is the coefficient of friction. So the coefficient of friction depends on the two surfaces in contact, and r, the normal reaction, will be determined by the mass of the object. So as said, the coefficient of friction will depend on the two surfaces in contact. The smoother and slippier the surfaces, the smaller the value of mu, and the smaller the value of mu, the smaller the value of the friction. As it says there, for two metal surfaces, mu might be about 0.2. For two wooden ones, it'd be about 0.4. Polished surfaces will reduce the value of mu. But there's no reason why mu cannot exceed 1. And remember, absolutely crucial, if the object is moving or about to move, or sometimes you might see a phrase, in limiting equilibrium, then friction is at its maximum, and the maximum value of friction is mu times r. Friction is useful to us. We may think it's not, but it's actually particularly useful to us because without it we wouldn't be able to walk. When walking, our muscles provide a backward force through our feet, so our back leg would be pushing backwards against the surface. If there was no friction, our back foot would just slide and we wouldn't be able to walk forward. It's friction that prevents the relative motion of that back foot and produces a grip that enables us to move forwards. So there's a backward force on the ground by the person, and there's a frictional force helping us to hold our back foot while we move forward. Similarly, we couldn't drive without friction. The mechanics of our car, the engine, will only turn the wheels round, and if the surface is very icy, that's all that will happen. The wheels will turn round, but the car won't move forward. Relative to the surface or the road, that wheel is wanting to move backwards, and therefore if it's rough ground, an opposing frictional force in the opposite direction, a forwards direction, will provide that forward motion. We're going to look at 3 examples here which emphasises that friction is a passive force and its maximum value will equal mu r. So in example A, the maximum possible value of friction would be mu times r, we're told that the value of mu is 0.3. So that's 0.3 times 2g. Now r must equal 2g because we're in equilibrium. Vertically, the forces will cancel out, so r must equal 2g. So the maximum value of friction is 0.3, which is mu, times by r, and that would be 5.88 newtons. Okay, now that's the maximum value, but in actual fact, because the pull force on this object is only 3 newtons, then friction does not need to be at its maximum. So in actual fact, since the pull force is only 3 newtons, friction will only equal 3 newtons in this case. If we pulled a little bit more, friction could increase, and it could increase all the way up to 5.88 newtons. But once you had a pull force greater than that, then equilibrium is broken and the object would start to accelerate. In part B, once again, vertically, r must equal 6g, so the maximum value of friction is mu times 6g, so that's 0.3 times 6g, and that's 17.64 newtons. The pull force is only 5 newtons, so friction only needs to be 5 newtons to maintain equilibrium. The pull force could increase all the way up to 17.64 newtons, and friction would increase all the way up to 17.64 newtons. Then that would be in limiting equilibrium at that point. If the pull force exceeded 17.64 newtons, equilibrium would be broken and the object would start to accelerate. In part C, once again, those are the forces. So the maximum value of friction is 0.3 times 3g, and that's 8.82 newtons. Okay, and therefore, because the pull force is 10 newtons, that's greater than the maximum value of friction. So friction cannot reach 10 newtons. Friction will only be 8.82 newtons, and therefore in that example in part C, the object would be accelerating. So we're in limiting equilibrium on a horizontal plane. Limiting equilibrium means that we're at the point where equilibrium is going to be broken, and therefore friction, it will be at its maximum because the object is just on the point of moving. Okay. So what are our sources of forces in this situation? Well, we have the weight component, the weight. We have the normal reaction, and it's a rough horizontal surface, so we will have friction. We wish to resolve the pull force horizontally and vertically. So horizontally, that would be the adjacent, so that would be P cos theta. Vertically, that would be the opposite side, so that's P sine theta. So now the forces on the object are vertically upwards, the normal reaction plus P sine theta. To the right, P cos theta, the weight, mg, and to the left, friction. And because because the object is on the point of moving, friction is at its maximum, so we know friction does equal mu r. Horizontally, therefore, mu r equals P cos theta. Vertically, we have r plus P sine theta equals mg, and then we'd be in a position, if we had a little bit more information, to start finding either P or theta, or indeed mu. And here's our example, where we now do have a little bit more information. Once again, our sources of forces, the weight, the normal reaction, it's a rough horizontal surface, so there's friction. The pull force we can resolve into its two components, 10 cos theta horizontally and 10 sine theta vertically. Therefore, if we put those forces on the object, r plus 10 sine theta upwards, to the right 10 cos theta, the weight, and friction. And because it's on the point of moving, friction equals mu r. So horizontally we have mu r equals 10 cos theta, and vertically we have r plus 10 sine theta equals 3g. Now, using those two equations, we have a more information. Sine theta is 3/5, so I have a 3, 4, 5 triangle there. That means cos theta equals 4/5. So equation 1 becomes mu r equals 10 times 4/5. So that's 8. Equation 2 becomes r plus 6 equals 3g. So we can find r from equation 2 and substitute that up into equation 1, and that will give us mu equals 0.342.